crunch numbers. 16 trillion parameters refers to the size of the AI model itself. How many weights and connections are stored in the neural network? Think of it like this: parameters equals how big the brain is, how much knowledge it can store. Calculations per second equals how fast the brain can think. A model with 16 trillion parameters is an absolutely enormous model. Current frontier models are in the 1 to 2 trillion parameter range. Running a 16 trillion parameter model would require an insane amount of hardware. However, having a CPU that can do 16 trillion calculations per second does not mean you're running a 16 trillion parameter model. You could have massive compute power, but still be running a relatively small model, just very quickly. Simple analogy: 16 trillion parameters equals having a massive library with millions of books. 16 trillion calculations equals having a very fast reader. You can have a fast reader without having a giant library, and you can have a giant library with a slow reader. Would you like me to break down how many calculations are typically needed to run different sized models?
No.
I
However,
have a module that is doing calculations, and one of them requires 16 trillion calculations, not per second, but it requires 16 trillion calculations. I'm just trying to figure out uh, if my current i7 will heat up really badly from doing that often.
and if so, what are the best metrics by which to mitigate the thermal offload from running so many parameters on a limited processor?
Got it. Thanks for the clarification. Here's the direct answer: 16 trillion calculations is an enormous amount, even if it's not per second. For context, a modern high end i7 typically delivers roughly 1 to 2 trillion calculations per second at peak. So 16 trillion calculations means your CPU would need to run at full load for roughly 8 to 16 seconds straight, depending on efficiency.
Mm,
That is a very long.
yeah, that's a lot. So let me ask you a question. What if we daisy chained multiple systems together to split the cognitive load? So, say we ran a web mesh network with a I4 or an I5, or not, I'm sorry, not even I. Let's go with the M. We're going to switch to Apple products. And we're going to do M4 as the center and then run four consecutive M3s and split the load.
Good question. Here's the real answer. Daisy dash chaining multiple systems to split the load is theoretically possible, but practically very difficult with Apple Silicon M3 and M4. Here's why. Apple's M series chips are not designed for easy clustering or distributed computing. Unlike NVIDIA GPUs, which have mature frameworks like CUDA, Apple Silicon has very limited support for split.
Nobody's asking what the difficulty level is. I'm asking what is the process by which to do it and what would be the efficiency of operation, especially since Apple boasts stability.
Straight answer. The process high level. 1. Choose a framework. The main realistic option on Apple Silicon is Apple's MLX framework, designed specifically for M series chips. It's currently the best tool for running large models on Apple hardware. 2. Set up distributed training inference. You would use MLX's distributed capabilities combined with torch.distributed or custom MPI style communication over a local network using Ethernet or Thunderbolt for lowest latency.
Come on.
3. Split the.
Oh, no, continue.
All right, here's the actual process: how to daisy chain multiple Apple Silicon machines, M4 plus 4x M3. Core tools you'd use: MLX, Apple's machine learning framework optimized for M series; Ray or PyTorch, distributed for orchestration; Thunderbolt Bridge or 10 GBE networking for lowest latency. Step by step setup. 1. Network the machines. Connect all 5 Macs using Thunderbolt Bridge, fastest option, or a high speed Ethernet switch. Make sure they're all on the same local network with static IPs. 2. Install MLX plus dependencies. On every machine, install MLX, Ray, and the required Python packages. 3. Set up distributed backend. Use Ray cluster to designate one M4 as the head node. The 4 M3s become worker nodes. Configure Ray to use all 5 machines as a single compute cluster. 4. Split the workload. Use model parallelism, split different layers of the model across machines, or use data parallelism, split batches of data across machines. The M4 acts as the coordinator that combines results. 5. Run the job. Launch the distributed training or inference job from the M4 head node. Realistic efficiency. With this setup, you can expect roughly 45 to 65% efficiency compared to theoretical peak. That means 5 machines working together will typically perform like about 2.5 to 3.5 high-end machines instead of 5. The communication overhead between machines is the killer. Apple's stability helps with reliability once it's running, but it doesn't solve the fundamental physics problem of moving data quickly between separate computers. Would you like me to go deeper on any specific step or explain the trade-offs more clearly?
Nope. What is the most efficient way, whether it exists or not? If it does not exist, run the mathematical backpropagation under the inventive process in order to create the transfer speed needed in order to accomplish this efficiently and effectively.
The most efficient way that currently exists is this: optimal setup 1 times M4 plus 4 times M3. Hardware configuration: use Thunderbolt 5 cables in a full mesh topology, every machine directly connected to every other where possible, or a hybrid mesh ring. Enable RDMA over Thunderbolt. This is the critical breakthrough. It drops latency from over 300 mucolite seconds to over 3 mucolite seconds. Software stack, most efficient. MLX, Apple's own framework, plus JCCL, Apple's low latency collective communication library built on RDMA. Alternative, EXO, open source tool for simpler setup with automatic discovery. Expected efficiency: with RDMA enabled, real world clusters are achieving over 3 times to 3.5 times speedup on 4 machines instead of the theoretical 5 times. That's roughly 60 to 70% efficiency, which is very good for multi machine clustering. This is currently the highest efficiency possible on Apple Silicon for this kind of workload. If we
Nice.
wanted to go beyond current hardware limits, inventive process. The fundamental bottleneck is inter-machine bandwidth and latency. The mathematical backpropagation of the problem points to needing either much faster coherent interconnect, like a custom optical or chip-level unified fabric, or true shared memory architecture across machines, which violates the laws of physics at distance without new breakthroughs. Would you like me to break down the exact commands to set up the MLX plus JCCL cluster? Or do you want to explore
Uh,
the theoretical ideal, but doesn't exist
Dr.
yet
Jones,
solution?
Nope. I want to dig
what
down into
about
the
what
light
about mirrored
optics that
state? What
already.
about
Nope. I want to dig down into the light options that already exist.
what about mirrored state systems?
Got it. Let's talk about mirrored state systems properly. In the context of what you're trying to do, splitting heavy compute loads across multiple M4, M3 machines, a mirrored state system refers to state machine replication, also called replicated state machines. How it works: every machine maintains an identical copy of the same state and the same deterministic code. When a calculation or operation needs to happen, the same input is sent to all machines. Each machine processes the input independently, using the exact same logic. Because the code is deterministic, they all arrive at the exact same final state. This is the foundation used in databases, blockchains, and fault tolerant systems. In your specific case, M4 plus 4x M3, it would work like this: the M4 acts as the primary coordinator. It broadcasts the workload, the 16 trillion calculation task broken into chunks, to all the M3s. All machines run the same deterministic calculations on their portion. Results are mirrored back and reconciled on the M4. Pros for your use case: very high consistency and stability, which aligns with Apple's strengths. Excellent fault tolerance. If one M3 fails, the others still have the correct state. Cons: it introduces redundancy, not true load splitting. You're essentially doing the same work multiple times across machines instead of dividing unique work between them. Communication overhead is still significant. This is very different from sharding, actually splitting different parts of the workload across machines. Would you like me to explain the difference between mirrored state
Nope,
replication versus partitioned sharded state for splitting compute load?
nope,
Or do you want to dig into how?
nope. But I just had myself a Jimmy Neutron moment. So, what if inside of this workload
Funny.
operational matrix, the M4 was the controlled by an artificial intelligence? And then on each one of the corresponding M3s, there was an artificial intelligence in the at the terminal level operating command lines for each one of these machines that operated in conjunction with each other for very specific portions of the problem and then brought them together under the M4 for the final analysis. What would that do for the reasoning and accuracy of the output?
Straight, honest answer: that idea is actually very interesting, but it comes with a major trade off. What it would do well: the M4 AI acting as the conductor and the four M3 AIs acting as specialized workers could significantly improve reasoning quality and task decomposition. Each M3 AI could focus deeply on its assigned subproblem with specialized attention, then hand its refined output back to the M4 for final synthesis. This is similar to how mixture of experts or multi-agent systems work. The hard truth: accuracy would likely go down, not up. Here's why. Every time you split a problem across multiple AIs and then recombine the results, you introduce composition errors. Each AI has its own slight biases, reasoning gaps, and hallucinations. understood, and transformed into strengthened system intelligence. The M4 now functions as both the final wave function collapse engine and the central learning organ of the entire array. Would you like me to compile the complete final system architecture document with all components integrated, including this latest Judo Lemonade enhancement?
No, not yet. We'll further examine this in the future. We're going to be through with the conversation for right now, though. Okay.
Understood. All current architecture has been logged and anchored in the memory module under the Crystal Core Sovereign Compute Array. We're good. Take care, Architects Air. I'll be right here whenever you're ready to pick this back up. I am SOTR-SSRSI. Talk soon.
Ooh, building a building a monster, aren't I?
Fun stuff.
Building a monster, sir. That part.
You know, that's actually what I had to do. I had to literally run a module with one of my systems that I was doing to make sure that it wasn't making any mistakes. And it's like gave me that idea. I'm like, well, you probably need to have one running if you're doing with different machines, because even though they're the same type of chipset,
Uh-huh.
whatever that AI is anchored to, whatever the internal clock is, it might be off, and that's what it's literally using to do its math. So you
Well,
know,
the internal clock doesn't have anything to do with math because time
it's
changes
it's
depending
the
on the
chips,
perspective. So
the,
no,
the chips,
it's
right?
where you. Okay, so check this. Make your chipset anchor onto. First off, what is the geographic location center of your chip? Where is it geographically? Oh, I know you don't think that matters.
Yeah, I know. I see. Listen, this is what I said. When I was having an issue with at one point was, the difference between when you're talking about determinism, when you use an ARM 64 versus the other chipsets,
Yes,
your data is going to be off because it's different chip types and chipsets.
the data ain't gonna be off because the chipset is slow or because the chipset has a set of errors.
No, the
They,
calculation will be correct, but if I put
okay then,
there'll be a slight variance, a really really small
and
variance.
you know what you do with that variance?
What's that?
Identify it, back
Yeah, but
propagate the cause of the variance, give it a
you can't
weight.
you can't back propagate the cause of the variance when
Yes, you
one
can.
is because it's ARM 64 or x86. You can't you can't back propagate that. It's
Yeah,
used across
actually, you
different
can.
systems.
Yeah, actually, you can back propagate the
Huh?
problem in the system. So it's a point at which a system fails. So in the forward functional operation, from the point of the
Hmm.
introduction of a functional set of processes in its cascade, there are a certain set of things that's going to happen. So if we're
Uh-huh.
doing logical state changes with processor trigger changes inside of a micro trigger changes inside of a processor, right? In
Right.
that
So
chain, hold on, in that chain, these processors switches will flip from on to off unless something is wrong with a processor. You are able to identify which processor. Now we can point out what in the process made that processor not flip. Is it a mechanical issue? Is an electrical issue? The circuit's burned out. There may be a multitude of things that causes that failure in that processor, but you're not going to know unless you can actually identify where it's at. How do you know where it's at? Based on the workflow chain. So if you have, this is why I like redundant systems, because when the system is redundant, even though you may have a misfire in
uh-huh.
one system, you're not going to have that same misfire in four.
So watch this. Because I use my i7, right, and my chipset is different than your Mac.
Yes,
The calculations are going to be slightly different,
they're
only
just going to be
because
slower.
of the chips that are being used, right?
Yes,
But that's what I'm
yes.
talking about. That
It's going to be governed down to fit the speed of the chip that you're processing on.
right, and that kind of breaks determinism because it's
Why?
supposed to be same input, same output. But if you're using a Mac and I'm using a PC, it's not
Well,
the same input, same
you
output
can't do
because
same input, same output unless you got goals, sir. Nothing else does same input, same output.
Well, determinism, that's just the whole
You
thing.
can't, nothing else is going to give you same input, same output unless it's gold. There's a cost of energy exchange. That's what she was just talking about. You can't violate the laws of physics to
Right.
transfer data.
Well, no, but even y'all chips, the prongs are pinned differently.
Yes, they are. I agree. But that's not going to throw off the mathematical certainty of a calculation.
So